Okay. So, we were discussing the Cauchy integral formula, and this Cauchy integral formula said that if f z be analytic in a simply connected domain, let f z be analytic in a simply connected domain D, then for any point z naught, in D, for any point z naught in D, and any simple closed path C in D that encloses z naught, the value of this integral f z over z minus z naught along the path C is equal to 2 pi I times the value of the function at a point z naught. That is, this is our domain D, z naught is this point and C is a curve which encroaches the point z naught lying in D. The direction is anti-clockwise direction, counter-clockwise direction. C is traversed in the counter-clockwise direction. So, the proof of this, we have already seen few examples based on this formula. Let us show proof of this. So, start with f z, which can be written as f of z naught plus f z minus f z naught. Clear? Now, substitute in 1, this is the formula. So, integral of f z minus z naught along the path C g z is nothing but what? F z naught is a fixed value. So, we can take it outside, integral C dz over z minus z naught plus integral along the curve C f z minus f z naught divided by z minus z naught dz. Okay. The first part of this is nothing but the f of z naught into 2 pi I, because this integral is a well known one, where m is equal to minus 1, the value will come out to be 2 pi I, whatever the closed path C may be. Okay. Means circle, C is a circular closed path, there is a simple closed path C which can be done. Okay. C is simple closed path. In fact, it can be transferred to the circle easily, because by deformation of the path, because if C is any closed path, suppose this is our C, okay, which is not a circle, it encroaches the point z naught, then the value of the integral along this path C will be the same as the value of this integral along this circle. Why? The reason is like this, that if we suppose picked up the 2 point here, then the value of the line integral from this to this is the same as the value of the line integral along this path by deformation of the path, because the function is analytic. Similarly, along this path the value will be the same as this path. So, value of the integral along any closed curve will be the same as the value of the integral along the circle centered at z naught with a radius say r. So, we can transfer and the value will come out to be 2 pi I. So, there is nothing to worry about. Then second part we wanted to show, this part will go to 0. This is our friend. So, second part we wanted to prove. So, what is our second part is f z minus f z naught over z minus z naught. So, let us see. Okay. Now, second part is integral f z minus f z naught over z minus z naught along the simple closed, any simple closed curve C lying in D and which encloses which encloses the point z naught. This was the given. We wanted the value of this integral will be 0. Okay. Now, if we look this function f z minus f z naught over z minus z naught. Now, this function is analytic except at z equal to z naught, that is all. So, the function, the integrand is analytic inside C except at z naught. So, if we look the function f z minus z, the numerator is analytic, but the point z naught is at this point the whole function is ceased to be analytic. Okay. Now, apply the principle of deformation. So, apply principle of deformation. Of path. So, we can replace C by, then we can replace C, the curved closed curve C, by a small circle K of radius say rho and center z naught. Why? This is our C, is it not? This was our C, because this curve C was this, okay, which encloses the point z naught. Now, by deformation of path, we are replacing this C by means of a circle centered at z naught with a radius say rho. This is the radius rho, and direction remains the same. This is, and this is possible because the deformation path. Because if I take two curve, as I told earlier, that if I take any point, join this one, okay, then if I go along this direction and come back along this and going from here like this, this domain, the function is totally analytic. So, the integral of this point, these 2 points along this path and the path in this direction will remain the same. So, this is what in this one, yeah. And here, if we take this integral from here to here, start from this, go like this and up to here, this integral of the function along this path will be the same as the integral along this red line, because throughout this the function f z minus f z naught over z minus z naught is analytic. So, this way by deformation form C can be reduced to this path. Similarly, this part of the C can be reduced to this portion. So, entire C can be reduced by a circle centered at z naught with the radius rho. So, that is what we have. So, by using the deformation of form, we can replace C by a small circle of radius rho and center z without altering the value of this. Okay. Now, further, since the function f z is analytic, so it is continuous also. So, it is continuous throughout T, hence at particular it is continuous at z naught. So, for a given epsilon, greater than 0, there exists a delta, positive such that mod of f z minus f z naught less than epsilon for all z in the disk mod z minus z naught is less than delta. Okay. Now, choose rho, because rho is our own choice. We can reduce rho as desired, okay, because it should not touch z naught, that is all. So, choose rho such that rho is smaller than, rho is less than delta, smaller than delta. Now, once you choose, then consider then mod of f z minus f z naught divided by z minus z naught. This will be strictly less because this part is less than epsilon. Z minus z naught is a circle centered at z naught with the radius rho. So, this is equal to rho. Okay. So, because z minus z naught mod is rho e to the power I theta, where theta lying between this. It is a circle. So, z minus z naught mod becomes rho. So, we get this, and this is true at each point of k, at each point of a circle k. This is a circle k. Okay. This is. Now, apply the ML inequality. So, now consider mod of integral f z minus f z naught divided by z minus z naught dz modulus of this along the path k. Now, this will be less than equal to, now this part is less than epsilon l, this is less than a, so epsilon l by rho, and mod of an integral of mod dz over k is the circumference of the k. So, this is the 2 pi rho. So, this becomes the 2 pi epsilon l, but epsilon l is arbitrarily small, but epsilon l is arbitrarily small. So, it goes to 0 as it can be. So, this will go to 0, is it not, as arbitrarily small. Therefore, second part is tending to 0. This not contribute anything. So, we get, so the integral of this curve, finally, we get integral of the function f z over z minus z naught along any simple closed curve C, which encloses the point z naught and f is analytic throughout, will be equal to 2 pi I times the value of the function. That is proved. Okay. So, this will be proved for this. Clear? So, this will now examples we have already seen. So, need not to worry. Now, in this is done for a simple connected domain, when D is a simply connected domain and C is a curve inside it. So, for a multiple connected domain, for multiply connected domain, for multiple connected domain, their Cauchy integral formula will take this shape. So, let us suppose if f z is analytic on C1 and C2 and in the ring shaped domain bounded by C1 and C2, C1 and C2, that is, this is our domain, that this is C1, here is C2. We are taking opposite direction here, C1 in clockwise, C2 in counterclockwise. C1 is counterclockwise, while C2 is a clockwise. C2 is clockwise. So, this is counter clockwise and here it clockwise. Direction is like this. So, suppose C1 and C2 are f is analytic on C1 and C2 and in the ring shaped domain this. Ring shaped domain this and Z naught B and Z naught B is any point in that domain. Then the value of the function at a point Z naught is equal to 1 by 2 pi I integral along the curve C1 of the function f z over z minus z naught dz plus 1 by 2 pi I integral of the function f z over z minus z naught dz along the curve C2, where the integral is outer is taken in the counterclockwise, inner is taken in the clockwise, and z naught is any point inside it. So, this gives the Cauchy integral formula for the multiple connected domains and similarly others. Okay. So, I think that is now there is one derivative of the analytic functions. So, before that let me take one of the examples. Yeah. Is that derivatives? Okay. Let us see this example 1 by integral dz over z square plus say 1 over the circle C, where C is mod z equal to 4, mod z equal to 4. Let us see this. Now, the function f z is 1 by z square plus 1, which is not analytic, at the point z equal to plus minus I. These are the point plus minus here z square plus 4, sorry, this is 4, z square plus 4. So, we get the mod z equal to 4, okay, plus minus 2 I, this is plus minus 2 I, 4. Okay. So, the singularities are lying here, z equal to 2 I, z equal to minus 2 I. The circle is centered at 0 with the radius 4. So, minus 4 plus 4 and here is something like this. So, this is our circle. Okay. This is our C, mod z equal to say 4. Now, the value of this integral we wanted this. So, if we look this function has two singularities. So, we can remove these singularities by drawing the two curves say C1 and C2, So, line integral along the pass outer boundary is the same as the line integral along the inner boundary. So, this will be the same as integral along C1 dz over z square plus 4 plus the line integral dz over z square plus 4. Okay. Now, C1 encloses the point 2i. So, basically the function z minus 2i 1 by z minus 2i over z plus 2i. So, if we break up z square plus 4 as z plus 2 I and z minus 2 I, then consider f z as 1 upon z minus 2 I, and then z minus z naught is this. So, it is C2. Okay, C2 encloses minus 2I. So, z equal to minus 2I, it is analytic, and for C1 you can write 1 over z plus 2I over z minus 2I along the path C1. So, if we write it this way, then what happens? This becomes a function f z which is analytic throughout the domain, is it not? Because C1, this C1 encloses only z equal to 2I. So, outside the function is analytic everywhere except this point. So, this is f z over z minus z naught. So, the value of this integral will be equal to 2 pi I times the value of the function 1 z plus 2 I at a point z equal to 2 I. And similarly, this also, this will be equal to 2 pi I, the value of the function at the point singular point z equal to minus 2 I. So, this total value comes out to be 0. Okay. So, we can get this value. Now, let us come to there is a further results for this Cauchy integral, that is the derivatives of the analytic functions. Now, we know if function f is continuous, then it may or may not be differentiable. But if the function is continuous and differentiable, then again we cannot talk about the second order derivative of the function of real, because it totally depends what type of the functions you are choosing. But in case of the functions of complex variable, if the function f is analytic, then all of its derivative will exist, and that can be established with the help of our Cauchy integral formula. So, the proof we are not giving, just we are giving the formula for the derivatives of an analytic function. This result says if f z is analytic, if f z is analytic in a domain D, then it has derivatives of all orders in D. Derivatives of all orders in D, which are then also analytic. In D, which are also then analytic in D. The values of these derivatives at a point z naught in D are given by the formula, given by f prime z naught is 1 by 2 pi I integral along the path C f z over z minus z naught whole square dz, and the nth derivative of f at the point z naught, the formula is given by this factorial n over 2 pi I integral along the path C f z over z minus z naught to the power n plus 1 dz, where n is 1, 2, 3 in general. Here C is a simple course. Here C is any simple closed path in D, any simple closed path in D that encloses the point Z naught and whose full interior belongs to D, and we integrate. The integration is taken counterclockwise. The integration is done counterclockwise. Integral is taken counterclockwise. So, what this result says is that if a function is analytic in a domain D, then all of its derivative of higher orders, all orders will exist, and they will also be analytic. And further, if we have the value of the function at a point Z naught by the help of the Cauchy integral formula, then the corresponding values of the derivatives at the point Z naught is given by this formula. The first derivative of prime Z naught is 1 upon 2 pi I integral C over C f z over z minus z naught whole square dz, and the nth derivative at the point Z naught is given by this formula factorial n over 2 pi I integral of the function f z over z minus z naught to the power n plus 1 over the curve C, where C is any simple closed path. The integration is taken in the counterclockwise direction, and the curve must enclose the point Z naught. Okay, lies in the domain where the function is analytic and curving. So, basically this is the form, but if we look this our Cauchy integral formula, then Cauchy integral formula is nothing but the value of this. This is our Cauchy integral formula, and integral f z over z minus z naught is equal to 2 pi I f z naught. Conditions are exactly same. So, if you want the first derivative, then it is easy to remember by just assuming that we are differentiating the whole thing with respect to z naught, keeping a thus variable constant. So, if I differentiate with respect to z naught, the right hand side become 2 pi I f prime z naught, and the left hand side f z is constant, z is constant. So, it is 1 over z minus z naught whole square into f z. That is what exactly we are getting. Then if we further differentiate, factor 2 sign come, and 2 pi I f z over z minus z cube, and like this. So, it is easy to remember the formula if we know the Cauchy integral formula thus. So, we will go the proof for one only, and rest will follow in a similar pattern. So, I will not go. So, proof of first part 1. So, what we have to prove is the derivative f prime z is nothing but this. Okay. What is the derivative? The derivative of a function at a point z naught is nothing but the limit of this f z naught plus delta z minus f z naught over delta z when the delta z tends to 0. So, this is. So, what we are doing is we are having this is a domain D, here is the point z naught, and this is a circle C. Okay. Now, if I look take a point, another point z naught plus delta z, which is very sufficiently close to this, then the function f will also be analytic at this point, and inside it encloses the curve C. This is the curve C. It is included, the curve C will also enclose the point z naught plus delta z. Okay. So, if we know the value of the function at a point z naught with the help of the Cauchy integral formula, then we can also find the value of the function at a point z naught plus delta z with the help of Cauchy integral formula. So, apply the Cauchy integral formula, or using Cauchy integral formula to get integral formula to get the value of the function f z naught and value of the function at a point z naught plus delta z, we get f z naught plus delta z minus f z naught divided by delta z divided by delta z. Now, this is nothing but 1 by 2 pi I delta z will remain as it is, and then the value of this integral f z over z minus the point z naught plus delta z dz along the path C minus the integral of the function f z over z minus z naught dz along the path C, because f of z naught is 1 upon 2 pi I integral f z over z minus z naught dz. So, replace z naught by z naught plus delta z z, we are getting this. Okay. Simplify it. Just when you simplify it, you will get the value will come out to be 1 by 2 pi I integral along the curve C f z over z minus z naught minus delta z into z minus z naught dz. Just simplify, you will get that with now. Okay. So, that will let it be one equation 2. This is 1, this is 2. Okay. Now, what we want is, we wanted to prove this part, that value of this integral f prime z is this. It means, when you take the limit delta z goes to 0, the limiting value of this, that is the limiting value of this, must coincide with this, or in other words, if I take this minus the difference of this, then as delta goes to 0, it must go to 0. So, now consider the difference of these two. So, if you take the difference of these integrals, because this integral, this is this integral minus the difference of this integral, is it not? So, consider this integral f z over z minus z naught minus delta z into z minus z naught dz along the curve C minus the integral of this f z over z minus z naught whole square dz. As delta goes to 0, delta 0, this must go to 0. But what is this? This value is nothing but what? F z over this thing, is it not? And then minus this. So, we get this part equal to, if I just take because this integral is the same along the same path. So, this integrand can be subtracted, and we get the integral along the curve C, which comes out to be f z dz over z minus z naught minus delta z into z minus z naught dz. So, this is finally. So, we wanted to show that this goes to 0 as n tends to infinity. Okay. So, our aim is to show, required to show is that this part, let it be this part third tends to 0 as delta z goes to 0. Okay. So, using the memory. Now, to show this thing, since f z is analytic, so f z is also continuous. F z is continuous on C. Once it is continuous, then it is bounded. Every continuous function is bounded. So, it is bounded on C, and once it is bounded in F z, therefore, there exists a constant k such that mod f z is less than or equal to k for all z. This is for all z belonging to C. Okay, for all z belongs to C. Okay. Now, let D be the smallest distance d be the smallest distance from z naught to the point of C. That is, this is our z naught, here this is C, C is any closed curve. Okay. So, this smallest distance is denoted by d, d is the smallest distance from this to this. Then for all z belongs to C, we have mod z minus z naught, which is less than equal to z minus z naught minus delta z plus this can be written as z delta z minus delta z. So, equality sign, and which is less than equal to z minus z naught minus delta z and then plus mod delta z. Okay. But z is an arbitrary point and d is the smallest distance. So, this is greater than equal to d, d is less than equal to this number this. Okay. So, from here we get d minus mod delta z is less than equal to z minus z naught minus delta z. Okay. Now, if I choose, let us choose z delta z mod of delta z is less than equal to d by 2. That is possible, because if z naught is here, I can choose the point here at z naught plus delta z in such a way that its absolute value is less than d by 2. Okay? Because the any point z here, any point z, this is the point z. So, mod z minus z naught is less than d, is greater than equal to d, because d is the smallest. So, if I choose any point z naught plus delta z, distance can be made less than d by 2. So, with this we can say, if it is there, then minus d by 2 greater than this. So, this part is less than half d is less than equal to this portion d minus delta z, because this is greater than equal to d minus d by 2, so and which is less than equal to z minus this and this. Okay. Therefore, from here what we get 1 over z minus z naught delta z is greater than this is greater than this. So, 1 by this is less than equal to 2 by d. That is simple. Okay. Now, use this thing for this part, because we wanted this third tends to 0. So, write down the third. Now, use third. So, what is the mod of third portion? Mod of third means mod of integral along C f z over z minus z naught delta z into z minus z naught dz. This is mod. Now, if you take mod, apply the ML inequality. So, this will be less than equal to mod f z is bounded by k along the path C. Z minus z naught mod of this is less than equal to 1 upon this is less than equal to 2. So, 2 by d. Z minus z naught is nothing but z minus z naught. This is just d, small circle. So, it is greater than equal to d. This is, so 1 by this is less than equal to d. So, again d. So, it is again d. So, 2 by d, and then this is yes, this will be d. Square will be there. I think that there is a left. I am sorry, this part will be equal to square. So, here square is left. I think we have made a mistake. So, here it will be square. So, this is d square and d square. Okay. Now, this approaches to 0 as delta z approaches to 0. Why? Because when delta z approaches to 0, okay, what happens to this? Delta z approaches to 0, then this mod of delta z is also there. Yes, this mod delta z, this is mod delta z, because dz is mod delta z, is it not? So, this mod delta z will go to 0 because rest are the constants. So, this will go to 0 and mod delta z goes to 0. Therefore, this integral will go to 0. This integral goes to 0, it means this limit will go to this limit, and once this limit goes to 0 means this limit will be equal to this. So, this implies that derivative f prime z naught is equal to limit z naught plus delta z minus f z naught by delta z tends to 0, and which comes out to be same as 1 by 2 pi I integral f z over z minus z naught square dz, is it not? So, that will be proved. Okay. The Cauchy integral formula, let us see few examples and then we go for that. Suppose we have this integral, say integrate the z to the power 4 minus 3 z square plus 6 divided by z plus I whole cube dz along the path C, where C is any closed contour enclosing the point z equal to minus I, okay, counterclockwise. So, if we look this function, C is any closed contour. So, z is equal to minus I, this is minus y, and C is this, which encloses the point minus I. So, obviously, the function z4 minus 3 z square plus 6 is an analytic function, but because of the z plus I in the denominator, total function ceases to be analytic at minus I, is it not? So, this is equivalent to f z over z minus z naught whole cube. So, if you look the formula for this, the formula for this says by Cauchy integral formula, the f of z naught, the nth derivative of function at a point z naught is nothing but factorial n over 2 pi I integral along the closed simple closed path C in D, which encloses the point z naught of f z over z minus z naught to the power n plus 1 dz. So, if we compare this integral with this, f z is this here, f of z is z 4 minus 3 z square plus 6, and what is z naught? Z naught is minus I, and n becomes 2, n becomes 2. So, basically this is the same as the f 2 z naught, the second derivative of function at the point z naught means I. So, if we take this curve, then the value of this equal to this is I, then the integral f z means z 4 minus 3 z square plus 6 divided z minus I power 2 plus 1 n plus 1 dz along the simple closed curve C, which encloses the point minus I, will be equal to 2 pi I times factorial 2, is it not? And then second derivative of this. So, second derivative of this function z 4 minus 3 z square plus 6, and then value of this as z is equal to what? Minus I, as z equal to minus I. So, second derivative of this becomes 12 z square minus 6 at z equal to minus I, and when you go for this, the value will come out to be minus 18 pi I. So, that is the answer. So, this way shows the value. Okay. Now, as a consequence of this Cauchy integral formula, we have few more concepts which are very useful. One is the Cauchy's inequality. Cauchy's inequality. What this Cauchy inequality says is, the modulus of f n at a point z naught is less than equal to factorial n into m divided by r to the power n, where we choose C in a circle center, where let f be analytic in a domain D which contains a simple closed curve C that encloses the point z naught inside it, okay, circle C, and let C is a circle. Suppose C is a circle which center which contains suppose here C is a circle of radius r and center z naught, okay, and center z naught. Then we have this result. The modulus of f n z naught is less than equal. Now, one more thing is also the function f z is bounded on C with m bounded on C. In fact, if it is analytic, it will be bounded also. Okay. So, let us see, the proof is follows from the what is our f n z naught, the nth derivative of f at the point z naught is equal to what? The formula says it is factorial n 2 pi I integral along the path C f z z minus z naught n plus 1 dz. So, take the modulus, apply the ML inequality. So, this is less than equal to factorial n 2 pi. Okay. Then now, mod of f z is dominated by m on C. So, it is less than equal to m. Then z minus z naught, because it is a circle we are choosing with radius r. So, r to the power n plus 1 dz mod of dz integral C with the circumference 2 pi r. So, we get this part, and which is nothing but what? R get cancelled, 2 pi get cancelled. So, this is nothing but what? Factorial n by r to the power n into m. Okay. So, this goes this one, that is this. Now, from here we also conclude another results which is known as the Liouville's theorem. Liouville's theorem. What this theorem says is, if an entire function f z is bounded in absolute value for all z, then f z must be a constant function. So, we can say in short that bounded entire function is always a constant function. So, this result also gives a one very important very important results, that is, if we take the sin z when z becomes real, it is a bounded function. So, sin x is bounded, cosine x is bounded, so far x is real. But when x is replaced by a complex, that is, function is defined over a complex field, then in that case the sin z becomes unbounded, because if it is bounded according to this result it must be constant. So, it contradicts that, because function is analytic everywhere theorem. So, let us proof of this is very simple. Now, in the previous case, in previous result, if I take n is equal to 1, then what happens there? Mod of f prime z naught is strictly less than what? M over R, but function f is entire function. So, f is analytic everywhere in the complex plane, but f z is entire. So, it is analytic everywhere in the complex plane. In the complex plane. Therefore, so take R as large as possible, infinity. Therefore, it implies that mod of f prime z naught tends to 0 as R tends. That is, f of z naught is constant, but z naught is arbitrary. So, we can say the f of z, but z naught is arbitrary. We can replace z naught, so the function f is constant. Because, okay, and the converse part of this is the Morera theorem. So, just I will give the result, which is the converse. If the function f z is continuous in a simply connected domain D, and if integral of the function f z along any closed path C is 0 for every closed path C in D, then function f z will be is analytic in D. This is the converse of the Cauchy theorem, Cauchy integral theorem. If the function is continuous in a simply connected domain D, and if the line integral along any closed path is 0, then function must be analytic in D. Thank you very much. That is all.